Hi, so we're going to continue with the chapter of Fourier series, a new subsection. So Fourier sine, cosine, complex series. Okay. So definition: let f be PC1 on 0 pi. So I'm giving a function that is, let's say this is my function that's only defined on 0 pi. The Fourier cosine of f is the Fourier series of the even extension of f, with the even extension, let's say, of sub e of f on minus pi. So what you do is you just extend f evenly, and then you get, this is f even, and then you calculate the Fourier series of f on minus pi. So how it's given? It's given by, so Fourier series, so the cosine Fourier series of f at x, by definition it is the Fourier series of fe at x, and this is equal a0 over 2 plus summation from n equal 1 to infinity an cosine nx. Why there's no bn? There's no bn because bn is fe sine nx, and this is even, this is odd, so the integral will be 0. What about a0? a0 is f even comma 1, which is equal 1 over pi integral from minus pi to pi f even at x dx. But I mean, this means that I have to compute f even. The thing is, I only have the formula of f, and I don't want to bother to calculate f even. But since this is an even function, this is 2 over pi integral from 0 to pi f of f even of x dx. So a0, but on 0 to pi, f even is the same as f. So a0 is 2 over pi integral from 0 to pi f of x dx. I wouldn't recommend to memorize it. I would do it step by step, like this, okay? What about a sub n? A sub n is f even cosine nx. And this is 1 over pi integral from minus pi to pi f even at x cosine nx dx. But f even is even and cosine nx is even, so the product will be even. So this is 2 over pi integral from 0 to pi f even at x cosine nx dx. But on 0 pi, f even is the same as f, which I know the formula from 0 to pi fx cosine nx dx. Why I'm doing this? Because I don't know the formula. Well, I can compute it, but I'm only given the formula for f on 0 pi. What about the Fourier sine series of f? It is the Fourier, so the Fourier is the Fourier series of the odd extension of the odd extension f odd of f on minus pi. And then this will be, you do the same, but now it is an odd, okay, this is this is, it is the odd extension. And what is the, if you say the sine Fourier series of f at x, I never use this, but I can see it in some of the previous or some of the sessions in the book. The Fourier series of f odd at x, I don't have a0 in this case. This will be n1 to infinity bn sine nx, and your bn will be f odd sine nx. And this will be, if you do as above, and again, don't memorize it, but for those who insist on memorizing it, please, for those who memorize it and do a calculation and write it wrong, then they get 0 points, okay? And you should show your work, and if you don't show your work, do it at least correctly. So this will be f of x sine n x dx from 0 to pi. An example, let f of x be equal sine x on 0 pi. So I have my function sine x, this is 0, this is x, and then find the Fourier sine series of f to find the Fourier cosine series of f, and 3, calculate summation from n equal 1 to infinity 1 over 4n squared minus 1, and summation from n equal 1 to infinity minus 1 power n over 4n squared minus 1. So this is x, this is z. Now 1. Now the Fourier sine series of f is the Fourier series of the odd extension of f to minus pi. And this will be in red. Okay. But what is this extension? If you extend sine oddly, you will also get the whole thing. Notice that what is f odd, by the way? F odd of x, this is equal to sine x on minus pi. Do you agree? I mean, this is the sine x when I extend it evenly. So the Fourier series of f odd at x is the Fourier series of sine x. But what is the Fourier series of sine x? It's sine x, because it's already a linear combination of sine and x and cosine and x. So that's the answer for the first question. What about the second question? The Fourier cosine series of f is the Fourier series of the even extension of f to minus pi. So this will be in blue. Now in this case, this is not clear what it is, but if you want to know, I mean, this is, I will write in scratch, you will not need it. F even of x is absolute value of sine x. Okay. This case. Now I need to calculate a0. So a0 is what? Is fe comma 1. So this is 1 over pi integral from minus pi to pi of fe at x dx. But this is even. This is 2 over pi integral from 0 to pi of fe of x, which is sine, well, which is sine x dx, because between 0 and pi my function is sine x, and this is equal to 2 over pi of minus cosine x between 0 and pi, and this is equal 4 over pi. This is a0. What about a sub n? This is f even comma cosine nx, which is equal 1 over pi integral from minus pi to pi fe at x cosine nx dx, and this is equal 2 over pi, because this is even now, 0 to pi. F even between 0 and pi is nothing but sine x, and this is cosine nx dx. Now you use that sine A cosine B is half sine A plus B plus sine A minus B, because it's sine A cosine B plus sine B cosine A. Okay, and it's minus sine B. This is correct. So this means that an is 2 over pi into integral from 0 to pi of 1/2. So this is 1 over pi again, sine 1 plus n x plus sine 1 minus n x dx. And now things, you should be very careful here. Now if I integrate this one, so I write in different color to know it's scratch. This is cosine 1 plus n x over 1 plus n with a minus. But this is true if 1 plus n different than 0, which means n different than minus 1. But this is okay because n is equal to 1, 2 is an integer. What about here? The integral of this is minus cosine 1 minus nx over 1 minus n. And this is equal, and now this is here. This is true for 1 minus n different than 0, which means n is different than 1. Okay? So, but now n can be 1, 2, 3 things. So I have different integral when n equal 1 and when n is different than 1. So we have to do it in 2 cases. So first, when n equal 1, in this case I get a sub 1. So do you understand why I have to take case n equal 1 different first and n different than 1 first? Because when n equal 1, this is the integral. Here, I mean, for n equal 1, I cannot use this formula. Okay? So a1 is what? Is 1 over pi, integral from 0 to pi, sine n equal 1, 2x, plus, for n equal 1, this is 0, dx. And now this is equal 1 over pi of cosine 2x over 2 with a minus between 0 and pi. And this is equal 1 over 2 pi of minus cosine 2 pi plus cosine 0. And this is equal to 0. What about when n equal 2, 3, and all these? Then you get an is 1 over pi, integral from 0 to pi, sine 1 plus nx plus sine 1 minus nx dx. And this is equal 1 over pi into minus cosine 1 plus nx over 1 plus n minus cosine 1 minus nx over 1 minus n between 0 and pi. Okay. Now this is equal 1 over pi into 1 over 1 plus n, and I will put a minus here, okay, because this becomes plus. When x equal pi, you get cosine 1 plus n times pi, which is, as you know, minus 1 power 1 plus n, because 1 plus n is integer. Okay. When x equals 0, we get 0. So this is minus 1. Okay. Plus 1 over 1 minus n of minus 1 power 1 minus n minus 1. Okay. And this you get here the cosine. Now you have two things. If you can notice that if n is even, if n is odd, this will be equal, n plus 1 will be even, and this will be equal to 1, and you get 0, and also here you get 0. So if n is even, it means n equal to k, I have a to k is equal to 0. Now if n is odd, mean n equal to k plus 1, but n is still what? Sorry. if n is odd, n equal to k plus 1, you get a to k plus 1. Here, this is 1. I mean, this is now even, so minus 1 power even is 1, so this is equal to 0. This is here for k equal, not 0, 1, because if k equals 0, you get a sub 1, and I'm not interested in a sub 1, I'm interested in a sub 3. A sub 1 I calculated separately. We are lucky that these two are the same. We are lucky, okay? And you had an example in the previous homework, which is, I think it was 3.2.2 part E, where these were different. Anyway, a to k plus 1 here for k equal 1, 2, 3, because for k equal 1 you start with a3. Now if n is even, it means n equal to k. A sub 2k is where k is 1, 2, 3, because I'm starting with 2, 4, whatever. It will be minus 1 over pi into 1 over 1 plus 2k minus 1 plus n, so this will be minus 2 plus 1 over 1 minus 2k into minus 2. Okay? And then you will get a sub 2k. I will put the minus 2 outside. You will get 2 over pi into 1 over 2k plus 1 minus 1 over 2k minus 1. Common denominator a to k equal 2 over pi over 4k squared minus 1. Common denominator, you get here 2k minus 1 minus 2k minus 1. And this is equal minus 4 over pi into 1 over 4k squared minus 1. And this is for n equal to k. Okay. I got my an, I got my bn. Well, my bn is 0. So what about my bn? Remember, bn is f even sine an x. But now this is even, this is odd, so the integral will be 0. Okay. So now what is the Fourier, was a cosine Fourier series of f, which is the Fourier series of f even at x. It's a0 over 2. What's a0? 4 over pi, so it's 2 over pi plus, now since the a1 was calculated separately, it's a good practice to do a1 cosine x plus summation from n equal 2 to infinity an cosine nx. These two, I mean, you calculated a1 in a different way, use a different, not in a different way, I mean, use a different formula for the antiderivative. So this is 2 over pi, a1 is 0, this we are done with this, then plus summation, only the even term survive, which is k equal 1 to infinity, and here minus 4 over pi cosine 2kx over 4k squared minus 1, which is Fourier series of f even at x equal 2 over pi minus 4 over pi summation from k equal 1 to infinity of 1 over 4k squared minus 1. Okay? And I have, sorry, cosine 2kx. And now we get the Fourier series. Now question 3 was calculate summation from n equal 1 to infinity 1 over 4n squared minus 1. This is part A. Part B, summation from n equal 1 to infinity minus 1 power n over 4n squared minus 1. Now I will do part A. Part A, you can do it using 201. Why? Because 1 over 4n squared minus 1, you can write as 1 over 2n minus 1 into 2n plus 1, and then write it as A over 2n minus 1 plus B over 2n plus 1, and then use telescopic series. Okay? This is using 201. Now using math to 12, Well, it's smarter to use, I think, you math to 1 in this case. I mean, you don't have to calculate the Fourier series in order to calculate the sum. But if you have the Fourier series, you just replace x by 0. Okay. But replacing x by 0, I need to use a convergence theorem. Now, since f even is PC1 and x equals 0, you should replace x here by 0 to get 1 over 4k minus 1. X equals 0 is a continuity point of f even. Then the Fourier series of f even at 0 equal f even at 0, which is equal f at 0 equal to 0. This is a sine x. But what is the Fourier series of f at 0? This is 2 over pi minus 4 over pi, summation from k equal 1 to infinity. You replace x by 0 of 1 over 4 k squared minus 1. Again, here when I say f even at 0, I mean the even extension. Okay, it's good. Even extension and 2 pi periodic. You always do it 2 pi periodic. And this is equal to 0. This means summation from k equal 1 to infinity of 1 over 4k squared minus 1 equal 2 over pi times pi over 4 equal to 1/2. Okay. Let me check. Okay. So 2 over pi times pi over 4. Okay. What about part B? Now part B is not a telescoping series. You cannot use 201 here. So I want to cosine 2kx to be minus 1 power k. But then what? Then you want 2k x to be, you want this to be k pi. So that you have cosine k pi is minus 1 power k. So you want x to be equal to, the k will cancel, pi over 2. So again, I use the convergence theorem at pi over 2. You have to justify, since fe is PC1 and x equal pi over 2 is a continuity point of fe, then Fourier series of fe at pi over 2 equal fe at pi over 2 equal f at pi over 2. Why? Because fe equal f on 0 pi equal sine pi over 2 equal to 1. And then this imply 2 over pi minus 4 over pi, summation from k equal 1 to infinity, cosine 2k, and x is what? Pi over 2 over 4k squared minus 1 is equal to 1. But this thing here is minus 1 power k. So you get summation from k equal 1 to infinity cosine, minus 1 power k over 4k squared minus 1 equal 1 minus 2 over pi into minus pi over 4. And this is equal minus pi over 4 plus half. Okay, and that's it. And that's the end of this part of Fourier sine, Fourier cosine. In the next video, we'll talk about the complex Fourier series.